Hello, everyone. I hope you all had a great day so far. Let's start today's discussion. Today, I'm going to go over the midterm assignment that we have. There is no basically a new concept that we are going to cover over the midterm. It's basically, you can consider it as a practice more than midterm. Because you already done those tasks, you already know the concepts. Probably it's just like different numbers. So it's just more of a practice than a midterm. So telling you that. So try to use your knowledge from the previous lab assignment, the first four lab assignments, and kind of like go over the midterm exam. And it's gonna be very easy to be honest. Okay. Now, that being said, you all probably already know that the canvas is down and there is no expected time that when the canvas is going to be fixed, and probably you're not going to have access to the canvas at least for today. Okay. Hopefully it's going to be fixed today and tomorrow you all have access. So in order to make sure that you all have the midterm assignment, every day until the canvas is fixed, I'm gonna provide the printed version of the file in the lab. So any one of you that have like the lab session today, if you go to the lab, there is a printed version for you over there, so you can pick it up and start going through the assignment. Now, one suggestion that I can make is that since all those assignment is you already done those kind of tasks, so you know what's going on. My suggestion is to do not postpone your pre-lab, okay? Sorry, you don't postpone the in-lab measurement to after you're done with the pre-lab. So you don't necessarily need to do the calculation before the measurement. So start your measurement. You don't lose any time in the lab because you have a limited amount of time in the lab. And you can kind of like run the calculation and simulation later. Okay, no, so this is one. Another one, I just find out that the Thursday afternoon, actually starting from 3 p.m., the campus is going to be closed. So I think this semester you are getting so lucky that we have to extend several assignments. So I probably have to. There is no choice. I don't like that, but I have to extend the midterm to next week. So instead of let me check the calendar. What happened to my calendar? Okay, instead of the 26th, your due time for the midterm assignment is going to be November 2nd. Okay, so good for you. Now, any question generally? November 2nd. So not this weekend, but the Sunday after this Sunday. And yeah,
Was there a way like in a stick out? So we can see one of the PDF stuff we can work on like without taking up the talking.
I will try. If I don't have access, like I don't have a collection of the emails, so I have to find every one of you singly and then copy your email. So it's gonna take a lot of time. Okay. So probably not today or tomorrow, but I will try to. Yeah, yeah, that's kind of like the hope. Probably it would, because it's nationwide problem. So every university has this same problem. But I try to uh, do that if I see that it's not going to be fixed in a near kind of like future. Okay. Any other question? Me too. you can come to the lab, but you have to plan. That's one, but I don't think you need the, honestly, the 4 hour lab session to do this, but I just want to make sure that it's a fair kind of like assignment. That's why I was standing that. So I don't believe you have a problem, even if you don't use this Thursday. Okay, so, but uh, uh, from 12 to 3 that we have lab session, the lab is going to be open. After 3, we have to close. Okay, yeah, this one. I am gonna have like next Monday. I wanted to like take advantage of this extension and talk about the PCB project, which is a voltage regulator. Okay. I am gonna cover how you can design it. You don't need to start right away because we are gonna cover the voltage regulator and the Zener diode the week after the midterm. Okay, so basically you can start in November. Okay, so but I'm gonna cover the concept and how to do that. Okay, and how you can have access to the either the Eagle Cat, which is one of the software that you can use for PCB design, okay, or Altium, which we recently got the license, and you can have access to my kind of like workspace to use Altium instead of the EagleCAD, which is more kind of like professional, and probably if you wanted to like do the industry, work in industry and design a PCB, you're most likely have to work with Altium rather than Eagle or any other PCB design software. Okay, did I answer your question? Any other question? No? Okay, let's start with the midterm lab, the midterm assignment. Now, exercise 1 covers the first lab basically when we wanted to like calculate the resistor, the equivalent resistor basically from a complex circuit. Now, I went through the curriculum that you are going to pass. You are already past the circuit 1 and other courses that you so far passed, and I assume, correct me if I'm wrong, that you are not introduced to the concept of the star and delta resistor impedance connection. No? Okay, so because that's one of the actually tricks of solving the first lab assignment. So take advantage of this assignment and learn that star delta transition. I'm going to talk about it right now. Okay, we have this complex network. If you want to use the regular parallel series formulas that we had for equivalent resistor, since we wanted to watch the equivalent resistor between the port A and B here, port A and B, basically you cannot distinguish any series or parallel connection. It's too mixed. Okay. Now, when you look at this loop here, okay, or here, doesn't matter, either one of them, okay, the formation of this sort of kind of like the formation of the resistor, we call it delta connection. Okay, now you might think, okay, what's the resemblance of this to the delta? Okay, now if you kind of like look to this on this loop very carefully, you can see, for example, the first loop, we have R1, very bad. We have the R1, okay, and then one side of the R1 is connected to the R3, and another terminal of R1 and R3 are connected to the two sides of R2. Do you see that? So now you can easily see the why we call this connection delta connection. Okay. Now there is a trick that we can use to kind of like transfer or convert this delta connection to a star connection. What's in a star connection? Let me use another color and kind of like drive this. A star connection is again three resistance that are connected in a way, let's say RA, RB, and RC. Okay, in a way that looks like a star or Y. Sometimes they call it Y connection. Okay, now if you run KBL and KCL through these two type of connection, which we are not going to go through, that is a very kind of like time consuming mathematical derivation, we can find that there is some formulas that we can, if we have a delta connection, we can find the equivalent star connection and replace it in a circuit. Okay, so in this circuit, we can replace one of the loops with the equivalent star connection. Then these resistors are not there anymore. We have an equivalent circuit, the star connection, that represents the same kind of like dynamic and electrical characteristics as that original delta one. Okay, now that you run this, now you can see it's very easy to find the R equivalent. You have two branches that have two series resistor, and then those two branches are parallel, and the result is going to be in series with the last resistor. Very easy. Now, how we can find each of these resistor based on the original delta in a star connection. I'm going to write the formula here. Let's actually do that. RA, if you want to find the RA, what you have to do, like you want to find RA, there is going to be a numerator and denominator. The denominator is the multiplication of the two resistance that are neighbors of RA. So R1 and R3. Okay? Are we good? The denominator is the summation of all the resistance. So R1 plus R2 plus R3. Now, I believe you easily can find or like assume that how we can calculate RB and RC is the same rule. RB is going to be the neighboring, the multiplication of the neighbors. So it's R2 and R3 divided by the summation. And RC is going to be again the multiplication of the neighbors, R1 and R2. And the denominator is again the summation. It's very easy to find those star connection, okay, resistor or configuration in general. Is that clear? How you can find the star connection and simplify your circuit? Are you good? Now, just for your information, I'm gonna also gives you the formula for reverse conversion from star to delta. It's gonna be handy, not for this lab assignment, but it's good to know. Okay, it's a very good knowledge. Now, if you wanna find the delta connection out of the given star connection. Now, what you should do is that, for example, we want to find R1. For finding that, it's a little bit trickier, or like has a very funny kind of like looking formula. The denominator for finding the R1 is the summation of multiplication of the pairs of resistors in the star connection. What I mean is we have RA, RB, and RC. So it's going to be RA, RB plus RA, RC plus what happened? Oh, RB, RC. The summation of multiplication of the pairs. Okay, this is going to be the denominator. Now, the denominator for finding R1 is the resistance in front of it. Which for this calculation, R1, the in front of it is RB. Okay, so this is how you can convert star to the delta. Now, let's complete our formulation. So R2 is going to be RA, RB, RA, RC plus RB, RC. And R2 is in front of RA, so it's going to be RA. And R3 is going to be RA, RB plus RA, RC plus RB, RC. And in front of R3 is RC, so the denominator is RC. Okay, so this is how you can convert delta connection to the star connection and a star connection to the delta. For this task, you only need to convert the delta to a star. Okay, but it's good knowledge to know how to you can go in a opposite direction. Any question? What do you mean? Okay, look at the connection. Look at this connection. Okay, R1 and R2 are connected at the same point. So basically, if you wanted to redraw this, I hope I can. This is gonna be a quiet of a. Oh, it's not gonna do a proper work. Let me replace everything. Okay, now this is point A. Okay, what you are gonna do is simply make this supernode to a node. Okay, supernode like kind of like connection. It's not actually supernode, but supernode like connection. So what you are gonna see here is same as this connection. Are you good? Is that clear? Now you have your delta, and now you can represent the values in the program.
So it's gonna be RC for this.
We want to see which one. Yeah, RC is gonna be here, and then there's. Okay. It's like I have a suggestion. Instead of like memorizing what I wrote, like I have a certain kind of like index, using index, like I use the bottom one, I introduce the bottom resistor at R2. It's not necessarily like a solid, way to show that. try to remember the rule of those equation. Okay, so when you wanted to like find the RA, it doesn't matter what is the name is. Okay, if you want to find this resistor, okay, the denominator is the multiplication of the neighbors. The denominator is the summation of all the delta resistors. You know what I'm saying? And if you wanted to do the star to delta, the denominator is the summation of the multiplication of the pairs. Okay, it doesn't matter what is their names. And the denominator is whatever resistor you see in front of that. You know, just this rule is better than, remembering the indexes. Any question? Good? Okay. Now, so you know how to, right now, you know how to simplify this circuit, and the rest is, I believe, very easy, probably like a 2-minute work of calculation. Okay, so for the in lab, again, what you have to, let me go to the deliverables. Okay, what you have to do is, first of all, you have your resistors. Okay, you need to, there are nominal values that I mentioned in a task. You already know that. You need to measure those values and find out what is the error and uncertainty. Okay, you have your R equivalent. Okay, calculation, you already know how to do that. For the measurement, again, you know how to use the multimeter to measure the resistance. The only thing that you need to do is basically connect the multimeter between these two and read the resistance. It's going to be the equivalent resistance. Okay, so it's very easy. You know how to measure error and uncertainty. For recalculating the R equivalent is the same again as we did before. There is no theoretical recalculation, so isn't it? Maybe it is. I don't know why I did that. This should be here. This should be filled, okay? It's a recalculation. So you have the actual values of the resistors, and again, you use the theoretical analysis to recalculate the value, the theoretical value of your equivalent resistor. Are we good? Okay, now. For the voltage and current and the power consumption of each of the resistor, okay, you need to have a 1 volt DC source. Are we good? 1 volt DC source. And then measuring the voltage across each of the resistors, you already know it's very easy, just using the multimeter. Okay. For current, you know, like for voltage, multimeter is in parallel with the equipment, with the component. For current is in series. I'm just repeating what you already know. When you wanted to do the power consumption, okay, for calculation, you need to actually run the analysis and find out what are the voltages and currents are based on the analysis. Okay. Based on that, you can calculate the power consumption. For measurement, you don't have a power meter. Okay, what you can do is, again, you are measuring the voltage and the current across the resistor. So you can use either one of the formulas for power, either VI or V squared over R or RI squared, either one of those formulas for power, and calculate your power based on your measured values. Okay? And errors and uncertainty is basically, you know how to do that. Any question? No, but for the measurement, you need to use the original circuit. You can use the star connection. Honestly, I wanted to say the other way, but since you just get introduced to that star delta kind of like transform, it's gonna be very kind of like challenging probably. Okay, so let's go for the star connection. Any other question? No? No. The second exercise is the transient response, or lab 3. Okay, and what we are going to do is to run the transient response with a step function 0 to 1 volt. Okay, 0 to 1 volt. I'm repeating because I have a purpose. 0 to 1 volt. Okay, pay attention to that when you setting your input voltage. Okay, and we wanted to like see if we have a 1K of resistor, 1K of ohm of resistor, and 0.1 microfarad of capacitor, what would be our transient response? And as you remember from the lab 3, what you need to calculate is, first of all, the time constant. Okay, very easy. It's just a reflection. And second of all, the values of voltage at tau, 2 tau, 3 tau, all the way to the 5 tau. You already done that. You have the formulas. It's just like replacing the numbers, to be honest. Okay. Now, in lab part, you need to use the oscilloscope. Okay. And you need to, again, measure, come on, measure the tau, which you know is the time that it takes us to go from the 0, when we leave the 0 line, okay, all the way until we reach the 63% of the final value. Okay, that's what you know. So you have to measure your tau, run the error analysis, find out how much error you have from measurement to calculation, and then run the uncertainty. Okay, now you're using oscilloscope. Remember, I wanted to like actually mention two comment over the calculation of uncertainty. Okay, one, if you calculating your uncertainty as 0, okay, you're not doing a good job. It's completely wrong. Okay, uncertainty is never 0. So that's comment number 1. Comment number 2 is that multimeter has quite a notable resolution. The minimum value that it can understand, okay, or show you is quite noticeable. For example, I believe like our multimeter or ohmmeter was 1 ohm, if I'm not making a mistake, or 0.1 ohm, I'm not sure. Either you need to like look at the screen and find out what is the lowest value that the multimeter can tell. Okay, now for oscilloscope, it's way lower than that. Okay, it's way lower than that because you have a voltage division that you can change. So when you talk about the resolution, you are talking about the minimum value when you set the resolution in an ultimate zoom in. You know what I mean? So, like, if you have the voltage division equal to 1, that's not your oscilloscope resolution. You have to decrease the voltage division all the way to the minimum that is possible, okay? And then find out what is the resolution of what is the lowest number that you can understand from that oscilloscope. Now, how to do that? If you zoom in too much, okay, basically you are not getting a continuous voltage. It's going to be a step, step, step instead of a continuous, like for example, sine. Those steps are basically the gaps, okay, or quantities that define the resolution of your oscilloscope, meaning within those numbers, lower than those step numbers, the step values, oscilloscope cannot understand or show you the numbers. Otherwise, it would be a continuous waveform. Make sense? Same goes for the time. When you calculating the tau, it's a time domain, not the voltage. Is on a time axis. So the uncertainty for tau should be calculated based on the time resolution, the minimum time resolution of your oscilloscope. Again, you need to zoom in all the way to the time, meaning decreasing the time division all the way down as far as you can go for based on your oscilloscope settings, and then see what is the lowest value that your oscilloscope can understand. Make sense? So remember, for the voltages, these are voltage. These are in oscilloscope, these are the y-axis. Tau is the x-axis when you calculate the uncertainty. Okay, now, let me actually add two other comments too. Another comment is that we said uncertainty, we have two types of uncertainty, type A, type B, and then we calculate the combined uncertainty with a 68% confidence, and we scale it up to 98% confidence. I hope you've already reviewed the video that I put, okay? I explained that on that video, okay? So, your type A uncertainty, when you using the multimeter, or most probably is going to be 0. Because if you do the 10-time reading of a resistor, I don't think you are going to see much any difference, okay, in your reading. So it's going to be 10 repeated reading, meaning there is all the data are equal to the mean value of the data set, meaning there is no standard deviation, so it's 0. So the type A is going to be 0. But you still have type C that you have to consider. Remember that. And if you have any variation in your readings, then your type A is not going to be 0. And when you calculate the U combined, remember it's a root mean square. You get what I'm saying? So it's UA squared plus UB squared under the square root. Okay, so. And another comment, if your uncertainty is too high, okay, because you can understand if you follow the formulas, you can see what it means. Like, for example, if your uncertainty is like 2 or 3, if you follow the uncertainty value, okay, you are going to see that means your standard deviation is quite high, because for multimeter, even for multimeter, which has a very low resolution compared to oscilloscope, the type B is still very low. So if you have a high value, the majority is going to be type A. that means your standard deviation is very high. The errors or accuracy of your devices are the type B uncertainty. It's bounded to type B uncertainty. That means the rest of the errors which created that high standard deviation between your data set is your mistake. Okay? That means you did something wrong. Either the connection was wrong, somewhere you missed one thing, and now you have a very huge standard deviation between your 10 kind of like data sets. Are we good? So please pay attention to these are meaning of uncertainty. That is why I put the uncertainty, include that in the task. So that way you can actually identify if you made a mistake. Are we good? Now, any question? No? So very easy. It should be very kind of like smooth process doing those two exercises. Now, exercise 3, which is the last exercise of midterm, is going to be the AC analysis. Okay? We actually trying to give you the feedbacks as soon as possible. We had a little bit of problem because of the canvas problem, but my plan is to give you the feedback. My original plan was to give you all the feedbacks for the lab 4 because you need it for this exercise 3. Probably like if you wanted to like see what are the mistakes that you did in the previous lab. My original plan was to give you by the end of Tuesday. But because of that problem, I have to kind of like work with the situation. It's not going to be affecting too much because I don't think it would take them like a week to fix the canvas. Okay. Otherwise, we are in a very kind of like bad situation, technology wise, you know. But since we already extended 1 week, I don't believe you should have any problem. You are going to get your feedbacks and have a proper time to actually incorporate those comments in your midterm. But to make sure, I'm going to go over the details of this, how to measure. The calculation wise, you already know. Okay, I don't think you have a problem for the calculation part. We already covered that. I already posted the lab solution and you had access to that. So you know how to calculate that. Okay, the only difference is that you have different inductors, and those of you that has a very small inductor, you are going to see a very small impedance for your inductor. That means your phase shift is going to be very small value. Okay, and basically the voltage across the inductor also is going to be very small value. Is a simple voltage division between the impedances. You already know how to do it. Okay, so if your inductor is probably like in a range of like 1 micron, I don't think we have less than that. In the range of like 1 micron up to 10, we probably would not be able to actually measure the time shift, the phase shift. Okay, because it's too low, it is within the oscilloscope resolution. Okay, so don't worry about that. You can see that, so it's going to be 0. But you already calculated. If you calculate that, again, you are going to have a very small number. Okay, it is going to be 100%, error, but that doesn't mean an actual error because you also have your uncertainty. Okay, so we can justify that. Does that make sense? Now, anyone, in order to like make that solid, anyone can tell me when I say I read, like, for example, one, yeah, 1 millivolt with an uncertainty of plus minus 5 times 10 to the power of minus 6 volt. Okay, what that means? If I tell you that my measurement is 1 millivolt plus minus 5 microvolt, okay, what's the conclusion that you can get, and what is going to be the exact value of the physical system that we have, the actual voltage that happened in visible world.
In the range. 1 mil plus it.
That is correct. Okay, but let me restate that. Okay, so we are gonna clear why I mean even if you have 100% error on that L situation, low L situation, it doesn't is not a big deal. Okay, so when I say I measured a 1 millivolt and my uncertainty at 98% confidence, which was what we are calculating, is 5 microvolt. It means, first of all, the exact value, the actual real value of the voltage, for example, across this inductance. What is actually happening on the circuit, not what you see or measure. The actual value. Is that clear what I'm saying? Okay. The actual value is not your measurement, but it is a number in the interval of 1 0.005 and this is going to be 0.995 millivolt. Okay, this is the interval for this number. But what that means is still we are not sure that the actual number is in this interval. I want you to pay attention to that. What that uncertainty means is that I can say I am 98% confident that the actual value is somewhere in that interval. Okay, 2%, it could be like 0 or 5. Okay, so I'm 98% sure that the actual value is within that interval. Is that clear? Now I wanted to like remember what we said. Like, for example, if your oscilloscope is 5 microvolt, it's going to be lower than that. But let's say it's 5 microvolt, or like for the time, because we are talking about the time shift, like let's say it's in 1 nanosecond, okay? And you measuring 0 for your time shift if you have a very low inductance. That means it doesn't mean you have 100% error. Okay, although you can calculate the error and it's gonna be 100%. Okay, but the actual meaning of that measurement is that you have a 98% confidence that your phase shift is somewhere between minus 1 nanosecond and plus 1 nanosecond. Are we good? So now you can see that actually that 0 means something. It's not just, okay, I couldn't realize that and it doesn't mean anything. Are we good? Okay. So you know how to measure, I hope actually, you know how to measure the impedance of this circuit. Again, you can review the video that I posted for the solution of the lab 4. What you have to measure and calculate is, first of all, is the impedance. Okay. For measurement, you can use your measured voltage and current. Okay. Does that make sense? Measured voltage and current. Voltage is across both R and L. Current, you can measure that with oscilloscope. Okay. You need to measure it using the resistor. Okay. So remember that. You already know what I'm talking about. Okay. So this is one comment. Now, I do have another way to actually do that, which because you have low inductance, I'm not suggesting, I'm not recommending that. But your multimeter also have a AC measurement for voltage and current. Okay, but since the resolution is too high, is the resolution that multimeter has is way above you probably see across the what you probably have to see across the L that you have. So I'm not suggesting that, but your multimeter also has an AC voltage and current measurement. For measuring that voltage measurement is going to be parallel with whatever component that you want to measure, and the current is going to be in series with whatever component that you want to measure the current through. Just remember the probes, they are different for voltage and currents. And for currents also, we have two range, which have two different sockets for the probes and two different option in the knob that you're turning. Okay, just pay attention to that. Okay. And DC voltage and AC voltage, you already know that they are two different settings. So pay attention to that. Again, for phase, you can use the phase shift in a current that you measure over the oscilloscope, which is going to be the phase of the voltage across the resistor. Is that clear why? Because the resistor would not change the phase of the current. So whatever phase you see in a voltage across the resistor is going to be the same phase of your current. Good. And the voltage across the whole impedance is the voltage source, which we consider zero. The phase is zero. So what would be the impedance phase? Phase of the current, the ohm law. Are we good? Now, measuring the voltage over the R and L, which you have to report the RMS value, okay? But for any reason, if you want to like report the peak value or peak to peak value, you need to mention, okay? Otherwise, your answer is wrong. Okay, so for current, again, you know how to calculate, and since this is series, you don't need to actually measure both of the currents for both of the component. If you measure the current through the resistor, it's going to be the same as the inductor. Okay, so another hint. And for the phase across the S and R, source and resistor and source and inductor, I'm going to be YouTube. You need to like use the two channels, one directly connected to the source, and another one, for example, directly connected to the resistor. We already talked about that. Whatever voltage you are going to see over the resistor should have the phase, okay, of the current. Okay, that means there any phase shift that you are going to see, any phase that you expect to see for the current is going to be the phase shift between the resistor and the source. Source phase is zero, is our reference. Are we good? And for the inductance, also the same. You just connect the probes, and you know how to measure using the cursors in the oscilloscope. You know how to measure the time shift, and you know how to translate that. You already have the formula to translate the time shift to the phase shift. Are you good? You had a question?
We expect
The value of inductance that we have is so low, okay, that like I had a 1 millihenry with inductance in my experience, and my base was like 1 meter. Okay, so you probably would not be able to see actually any based on your own inductance, which is going to be probably lower than mine. The majority of you have a smaller inductor than 1 millihenry. So it's going to be a smaller degree phase here in a current. That means we probably do not see any notable phase shift. But theoretically, yes, whatever phase the voltage across the resistor has is going to be it should be the phase shift between the voltage and the resistor and the current is going to be the phase of the current, which is the phase of the impulse. Any other question?
Send the volts this in currents.
The values of it. Any other question? No? Perfect. So if you don't have any question, we can end this session. Thank you very much and have a great rest of the day.